Hello friends, in today's lecture we will be studying the introduction to the subject known as FEA or Finite Elemental Analysis. So before introducing ourselves to this topic, let us understand the learning objectives of today's lecture. So first thing, we will be understanding the types of solving an engineering problem. Basically in this we will be understanding the three methods to get the solution of an engineering problem. Next, we understand the definition of finite elemental analysis in simple language. We will also be seeing the various definitions of finite elemental analysis from a mathematical point of view in terms of numerical methods. Then, we will be studying the key terminologies in order to understand the mathematical definition of FEA. Then we come to the concept of understanding meshing, which describes the geometry of a structure and helps us to analyze the material properties. In the concluding part of the introduction, we will learn the application and the need for finite elemental analysis in the industrial world. So, let's look at the big question, which is in how many ways do we solve an engineering problem? So, let's have a look into it. So, from the table, we understand that in order to solve an engineering problem, there are three methods which we use in our day-to-day industrial as well as educational purposes. They are namely analytical methods, experimental methods, and numerical methods. Each and every method has its own merits in order to solve every engineering problem. Let's look at each one of them. The analytical method is also called as the hand calculation method. It is a method in which we use the problem and apply a strategy in order to execute the solution in the best possible way. It is also the method which requires memorizing formulas and requires a lot of calculations. Basically, this method is the approach we use in our daily school and college lives in order to get the solutions like area, volume, force reactions, moments, etc. This also means that it is also used to execute problems with simple geometries. The following figure shows a truss in which we find out the moments and force calculations using the analytical method. Let's look at the next method. An experimental method is also called a physical testing method. It is so called as a testing method because it involves various experimenting of the engineering problems or a prototype, either in terms of a machine or a device in order to get a proper solution. One major advantage of this method is that it can be used when the machine is in operation and did not be stopped in order to find a solution. For example, we use an accelerometer to find out the vibration of any machine. We also use the Brinell testing machine to check the hardness of any material. We also have used the governor, the gyroscope, vibration model apparatus in our lower engineering classes. So any experimental method requires 3 to 4 testings in order to be done on a material or a machine in order to come to a proper conclusion of the problem. This method is time consuming and expensive. So let's go to the next and the most important method for the topic finite elemental analysis, that is numerical methods. This method deals with a lot of high-end software techniques in order to find a solution to the problem. In real life, we use a mathematical model in order to represent the structural model along with the conditions it faces. The real life conditions which a structure or body faces is called as boundary condition. The method does not require a physical prototype model. Also, it does not require a working model to get the solution to a problem. This method works on a lot of assumptions and requires some analytical or experimental methods after getting the solution. We also use various softwares such as ANSYS, Dune, Elmer in order to understand how a product works when it faces forces, vibrations, fluid flow, and other physical aspects. In order to solve a problem in engineering, the numerical method is divided into various types such as finite difference method, finite elemental method or FEA, which is finite elemental analysis, weighted residual method or boundary element method, which is called as BEM, and finite volume method, which is called as FVM. So, a numerical method is a method in which we use high-end software-based techniques with approximations. In this technique, we do not need a physical model or a prototype. This method also involves lots and lots of assumptions. Usually, this method is used for complex geometries. Also, the solutions which we get from this have to be tested by the experimental or the analytical method. The various types of numerical methods are FEA or FEM, WRM or BEM, which is the weighted residual method or boundary elemental method, or it can also be called as FDM or FVM. We use various softwares such as ANSYS, Dunes, Elmer in order to understand how a product works when it faces forces, vibrations, fluid flow, and other physical aspects. In order to solve a problem in the engineering, the numerical method is divided into various types such as finite difference method, which is FDM, finite elemental method or FEM, or FEA, which is finite elemental analysis, weighted residual method or boundary element method, and finite volume method. So, let's have a quick recap on all the three methods we use to solve an engineering problem. So, if we get into the analytical method, we understand that the analytical method is a hand calculation method. It has the most accurate answers to a solution. It is used only for simple geometries and it can be used for beams and trusses in our day-to-day life. Then in the next method, which is called as the experimental method. So as the name suggests, we have to go for the physical testing of a prototype or the model. It requires 3 to 4 tests for the accurate results. It is also accurate while the machine is operating. This method is time consuming, whereas also it is very much expensive. Now let's take a look at the numerical methods. The numerical method is a software based technique. It is also required when you are testing a physical model. This method requires lots of assumptions and can be used for geometrical properties. And this method can also be used for complex geometries. And this is the way we go for the ANSYS technique. So generally we have many definitions for FEA. If we go through the various books on this topic, we understand that there are many complex definitions for a simple concept. Below is the concept of the understanding we should have for any FEA problem. In simple terms, we will be given a body or a structure with any complex geometry. We definitely cannot get the solution to any of the complex problems using the analytical or the experimental method. Hence, we will break down the problem into smaller parts. Then we study each broken piece by applying the various numerical methods. After getting the solution to each of the broken pieces, we integrate them or assemble each one of them to get the solution to the original problem. So, as per the simple concept we learned in the previous slide, we can define FEA as the methods of breaking a complex geometry into smaller geometries or shapes and solving each one of them to get a linear or accurate solution by assembling the broken pieces into shapes or geometries. So, as per the simplest definition of FEA, we understand that FEA is nothing but breaking a complex geometry or shape into smaller geometries or shapes and solving each one of them to get a nearly accurate solution by assembling the broken pieces or geometries or shape. Now, let's look into the key terminologies. First is discretization. Discretization of a domain is the process of subdividing the domain into smaller parts called as finite elements as per the requirements and the convenience. The main purpose of this is to solve the complex geometry through finite elements. In the figure, we have been given a domain in the shape of a trapezoid. This shape can be called as a domain. Now, if we are asked to find out the area of a trapezoid, we can divide the trapezoid or the domain into three parts. One is a triangular element, second is the rectangular element, whereas the third is again the triangular element. So, namely, we can say that the trapezoid or the domain has been divided into three parts or three elements. Now, if you observe carefully, you can understand that there are some points where the elements are connected. These points are called as nodes. Now, let us understand what are elements. In finite elemental method, complex geometry is divided into simple geometric shape called as finite elements. There are also various types of elements. In the previous example of a trapezoid, we had divided the domain into three parts, which are two triangles and one rectangle. As I said, an element is divided into three types, that is, one-dimensional element, two-dimensional element, and three-dimensional element. In the next few topics, we will be understanding each and every type of element and their benefits for getting a solution. Now, let's understand the meaning of nodes. The endpoints of an element are called as nodes. In this example, consider I am drawing a bar and the starting point is 1 and the end point is 2. In the middle of the bar, I consider an element which is nothing but small e. The nodes are denoted by 1 and 2. The number of the element is specified by e. The left hand side of the node is 1 and the right hand side is called as 2. The nomenclature refers to a particular element within the domain over which the element stiffness matrix is developed. However, the nodes are developed in the global coordinate system. Now, let's look at the degrees of freedom. In the diagram below, you can see three figures. In the first figure, I am having point A, and point A is restricted to a plane. So, if I want to define the position of point A with respect to x-axis and y-axis, I just have two axes with me right now. So, I can define the point A in terms of its x coordinate as well as in terms of its y coordinate. Now, if I take the second figure, in this point A has been transferred to point B. Now, I am having three coordinate systems in order to define its change in position. One is the x coordinate, second is the y coordinate, and the third is the rotation of point A to point B. Now, let's look into the third diagram. In third diagram, I am having namely three axes. One is the x-axis, second is the y-axis, whereas the third one is the z-axis. Now the point A can move in three axes, which is the x, y, as well as the z. Now, in order to define the coordinate of point A, I can say that we have six coordinates, which are x, y, z. X, y, and z is nothing but the translation motion. Ux, uy, and uz are the points in which the point A can rotate from point A to point B in x, y, as well as z axis respectively. Hence, let's look into the degrees of freedom. In simple words, degrees of freedom is nothing but the possible way in which a body can move. The minimum number of parameters required to define the position of a body is called as degrees of freedom. So in the first figure, we saw point A is having 2 degrees of freedom. In the second figure, we understood that it is having 3 degrees of freedom, that is 2 translation motions and 1 rotation motion. And in the third figure, we saw that it has 6 degrees of freedom. I can write it as 6 DOF because it is having 3 translation motions and 6 rotatory motions. Now, let's look at the degree of freedom of a body in space. Now, if I talk about the space, we know that space can be defined in terms of its 3 axes, which is namely x-axis, y-axis, and z-axis. If we consider a point A anywhere in the position of this given point, now I know that whenever I define a point in the space, it is not restricted to any of constraint. So I can give the point A total 6 degrees of freedom. Namely, point A can move in the x direction, in the y direction, as well as the z direction. Hence, it is having 3 translatory motions which symbolize 3 degrees of freedom. But as I said, point A is just not restricted to the plane. So it can also rotate about the x-axis, it can also rotate about the z-axis, also it can rotate about the y-axis. So for a point in a space, we can say that a point will always have 6 degrees of freedom, which are 3 translatory motions and 3 rotatory motions. Now, let's understand the degrees of freedom of a body in a plane. Now, if I take any plane which has been restricted to the x-axis as well as the y-axis. Again, if I take any point which has been restricted on the plane which I am having a constraint, I understand that the point A can move only about the y-axis and only about the z-axis. But point A can also rotate about the z-axis. Am I clear with this part? Yes. So I can understand that point A is having 2 translation motions and 1 rotation motion. So total I am having 3 degrees of freedom. So I can say that for a point in a plane, the point always has 3 degrees of freedom. So let's look at another definition for finite elemental analysis. If we go for the point, so if I talk about finite, finite means nothing but reducing the degrees of freedom from infinite geometries to finite geometries. So what are we doing? We are reducing the degrees of freedom. Second is element from the part E. We can say that all calculations are inferred from limited points called as nodes. The boundary joining the nodes form a specific shape such as quadrilateral, triangle, etc. And if I talk about A, it is nothing but the study. So FEA also means reducing the geometries or reducing the degrees of freedom. And when I talk about method, it's obvious that this method comes under numerical method study. So let's define it again. In various definitions, we can also say that it is nothing but reducing the degrees of freedom or DOF from infinite to finite parts or sections with the help of discretization or meshing techniques using the nodal or the elemental analysis. Now let's look into another concept. If I say FEA, F stands for finite or countable, E stands for element or part, and A stands for the study of domain, of course. Now, if I've been given a bar which is under some load P, and if I have been asked how to find out the deflection, in the analytical method, what we do is we go for the matrix equation of the whole beam. But getting accuracy in this part is a big major concern. But if we go for finding out the deflection using the FEA method, the first step we use is the discretization method, discretizing the domain into equal parts or equal elements. So once we discretize this part with the load P, the first step we do is discretizing it. Now we go for the matrix equation of the individual parts or elements of the beam. Next, we go for the integration of all the answers that we get from the matrix equations. Due to this, what happens is we get a very accurate answer. Hence, if we go for the mathematical definition, we understand that FEA or finite elemental method is a numerical method to solve the various complex engineering problems using an array of mathematical techniques. So hope you have understood the definitions of FEA. Now, let's understand a very important concept which is called as meshing. In the figure, what you can see is, you can see two bottles. One bottle is a plastic bottle, second is a steel bottle. On applying pressure on both of these bottles, we can see that the plastic bottle can get crushed easily. Whereas, if we try to crush the steel bottle, it is not possible to do it. But why does this happen? This happens just because of one geometrical function of every material which is called as meshing. So, in meshing, we can give any material a property of our own. If we look into the plastic body, we gave the quality of plastic. Hence, we can break the plastic or we can also burn the plastic. But when we give this bottle the quality of steel, we cannot bend it. Hence, meshing gives us an upper hand over choosing the geometry or choosing the material of any of the bodies. Now, let's look into the application part. If you see that for any car model, we have to go for the damage analysis, in which we dash or we bang. In the car crash model analysis, what we do is the company damages a car and spends a lot of money on it. So, if we look into the car crash model analysis, a company goes for crashing of a car using various dummies. This costs a lot of amount of money for them. But if we use the FEA model, we can go for the boundary conditions and we can save a lot of money. Hence, by using the boundary conditions, we can understand the forces which act on the car, and we can also understand the damage control a car has to go through. So this was the introduction part to finite elemental analysis. Hope you have understood all the concepts. Thank you for watching this video. Stay tuned to Ekeeda and do subscribe our channel.